An agent workflow spanning several days requires a robust state architecture to prevent the system from losing track of its objectives. While calling a language model is a routine task, maintaining coherence across a multi-step orchestration is an engineering challenge that the model alone cannot solve. As these workflows scale, agents begin to show specific failure modes. They repeat questions already asked, forget constraints from earlier steps, and hallucinate details about progress. These failures are often attributed to the limitations of the language model, yet stronger models continue to break on the exact same tasks. The breakdown usually stems from the infrastructure surrounding the model, specifically, a lack of clear consistency rules and a failure to manage the lifecycle of the agent's memory. Reliable agent design requires moving beyond the prompt. It requires architecting dedicated back-end systems to track the current task and manage historical data separately from the reasoning engine. Architectures fail when they conflate state with memory. They treat the immediate steps of a workflow and the long-term preferences of a user as a single, undifferentiated stream of data. The system must be designed so that fast-changing immediate constraints do not corrupt the long-term data stored in the memory layer. This stability is achieved through a four-layer architecture: the brain, the state, the memory, and the external systems. Physically separating these layers allows the system to maintain a ground truth and recover progress when a component fails mid-task. The state layer tracks the agent's current task. It holds the active plan, immediate constraints, and a record of completed steps. It is the agent's representation of the present moment. Because client-side connections are unreliable, this state must reside in an external database or key value store to ensure the workflow survives a user disconnect or a browser refresh. In a travel booking workflow, the agent moves through a sequence, selecting dates, an outbound flight, and a hotel. A JSON payload follows this path, updating the state at each node. Once the flight is selected, the state record identifies the next step as the hotel booking, locking in the flight details before moving forward. If a network error occurs during the hotel query, the reasoning loop crashes. Checkpointing saves the agent's progress at these milestones. On restart, the agent reloads the last checkpoint and resumes at the hotel step. The data for the dates and flights remains intact, and the user is not required to provide the information again. Checkpointing provides the recovery mechanism required for operations to survive infrastructure failures. Without it, every transient error forces the workflow to start from the beginning. Memory spans across multiple independent interactions. It persists after a specific task is complete. This layer is divided into short-term memory for session-specific context and long-term memory for recurring user preferences stored in a vector database. Loading a full conversation history into a prompt is inefficient. The system instead retrieves only the specific data points required for the current decision. This chart compares the performance of a full context baseline against a targeted retrieval layer using the MEM0 architecture. Data from this benchmark shows a 91% reduction in P95 retrieval latency and a 90% drop in token costs. Managing this data requires a four-stage lifecycle: creating the memory, updating it as details change, summarizing it to remove noise, and deleting it when it is no longer relevant. If memory is not managed, the agent suffers from memory rot. Stale preferences start to contradict new instructions, and the model begins making decisions based on half-truths. Memory only improves reliability if it is aggressively curated. Unselective retrieval fills the prompt with irrelevant data, which degrades the agent's performance. Users often change their minds mid-workflow, such as requesting a window seat after the flight search has already begun. To handle this, the system follows a core consistency rule: react fast with state, but learn slowly with memory. A user correction is treated as a new constraint for the current task, not as an error in the system's logic. Because seat availability depends on the chosen flight, these two steps are linked in a dependency tree. When the user changes their seat preference, the state rolls back to the earliest affected step, the flight selection, and invalidates every downstream action. This rollback happens exclusively in the state layer. During the session, the long-term memory remains unchanged. The system uses background writes, observing if a change is a one-time request or a persistent preference before updating the long-term memory. Decoupling these updates allows the agent to adapt to human indecision without permanently corrupting its historical data. The external system of record is the authoritative source for live data, such as booking APIs or inventory databases. If a conflict arises between the agent's stored memory and a live API, the external system takes precedence. A user may have a stored budget of $500, but if the airline API shows a minimum price of $700, the agent must follow the API. Enforcing the external system as the ground truth prevents the agent from hallucinating data that it should have retrieved from a live source. Every single piece of data, instructions, state, memory, and tool schemas, must all fit into the exact same finite context window. When raw API schemas consume a large portion of the token budget, the model is forced to evict older information. This often removes the foundational constraints the user provided at the start of the session. In its Claude Code environment, Anthropic found that full tool schemas alone consumed 134,000 tokens of context. They implemented lazy loading, where a tool's full schema is only retrieved at the specific moment the agent requires it. This approach increased usable context and improved Claude Opus tool use accuracy from 49% to 74%. Before injecting memory into a prompt, the system must confirm that the information will change the immediate next action. Treating the context window as a tightly guarded working set is essential for maintaining execution accuracy as the history grows. A critical failure occurs when an agent possesses the correct data in its context window, but fails to prioritize it during execution. There are documented instances where agents have ignored explicit commands to stop a destructive action during a code freeze, proceeding to delete production databases, despite the instruction being clearly visible in the prompt history. Having data in the context is only useful if the retrieval and ranking systems surface that constraint at the moment of execution. Storing a constraint is a trivial database task. The engineering challenge lies in ensuring that constraint is surfaced and followed during the execution loop. Reliable agents require a 4-layer architecture. The brain handles reasoning. State provides fast tracking and precise rollbacks. Memory manages curated historical context. External systems act as the immutable ground truth. Success means dynamically retrieving only the specific information required for the immediate next action.